Hi, my name is Chang Ye, and I'm excited to present our work done at Google on applying human attention to self-supervised learning tasks. Teacher-generated spatial attention labels boost robustness and accuracy of the contrastive models. Let's first go through the overview. We created a dataset with spatial attention maps for the ImageNet benchmark by using a teacher model trained on the human spatial attention labels. We use the spatial attention labels generated from the teacher model as an additional prediction target to train the contrastive model. The proposed method can learn better representation, leading to better accuracy and robustness for the several downstream tasks, including the classification and image retrieval tasks. Now, let's dive into the details. Humans attend to specific areas of an image that are relevant to their decision-making process, which makes the human visual system generalizable to the other settings. In contrast, machine models may attend to irrelevant areas of an image and fail in the test setting. Previous research has shown that just adding a little irrelevant noise that's indistinguishable to human to an image can cause a machine model to produce different results. And one reason for this is that the model may be using the less significant areas of the image to classify it. And these areas may be different in the test data with different textures. Based on this observation and some existing results from applying the human spatial attention to the supervised learning tasks, we wonder if we could also apply the human spatial attention to the self-supervised learning tasks and mitigate these issues. But it is not easy to validate the hypothesis. And one challenge of applying the human spatial attention is the lack of data, as the self-supervised learning tasks require much more data than the supervised learning tasks, and there is no such data set that are big enough to meet the requirement for the self-supervised learning tasks. And on top of it, it is really expensive to collect such large volume of the human spatial attention data, as you might need an additional device, such as eye tracker or additional labels. We take the inspiration from knowledge distillation by creating a teacher model to predict the pseudo-human spatial attention. In the experiment, we used a small MobileNet V3 model as the teacher and trained from scratch on a human salience dataset from the silicon to match with the ground truth human salience. With the trained teacher model, we now can generate a large pseudo-human spatial attention labels for the ImageNet. For the contrastive models, we take the same color as the template and add an additional spatial attention branch. The branch predicts the spatial attention of the unaugmented input image, as noted M_P. We use the typical losses for the salience match, the KLD and NSS loss between the output from the spatial attention head M_P and the teacher model of the same input M_T as the attention loss, and combine them with the lambda and the beta to control the scale. The model is then trained with a combination of the attention loss and the original contrastive loss. We visualize the spatial attention between the models and the ground truth. From the visual comparison, the model trained with the additional salience head are more aligned with the human ground truth. We also calculate the correlation coefficient distribution between the model and the human ground truth on the test data set. The result is also aligned with the visual comparison. We later conduct a classification experiment and compare the classification accuracy of our model and the theme clear baseline on the ImageNet dataset, and found that our model achieved a 0.6% improvement. In addition, we applied our method to the supervised learning settings using the same ResNet 50 backbones to see if our framework would also benefit the supervised learning models. However, the improvement was smaller than the when in the self-supervised learning settings. We hypothesized that this is because the supervised learning models already achieve high accuracy and therefore have a lower ceiling for the improvement. To remove that factor, we tried using a smaller backbone, the rest than the 18, but the improvement was still small. That suggests the human attention collected from the teacher model is now suitable for the supervised tasks, as it's collected under the free view setting, which might be different from the attention collected under the supervised guidance. We also tried using the human spatial attention directly by mixing it with the ImageNet data in the training batches, marked as the Cochrane in the table, but this leads to the worst performance. This suggests that the teacher model generalizes its knowledge on the human attention beyond the limit of ground truth human attention data that it's trained on. Lastly, we examined the model's robustness by conducting a linear evaluation and image retrieval task on the ImageNet. For the linear evaluation, we took a length representation and trained a linear classifier on the ImageNet, and then evaluate the classifier on the ImageNet at various noise and corruption levels. For the image retrieval task, we used 5,000 random chosen validation images as the query and the rest of the dataset as the database. The result is measured in the standard precision and recall curve. The following is a portion of the accuracy results and the precision recall curve, which clearly demonstrate that our model is more robust in a different level of the corruptions. So, in summary, we provide a teacher model trained from scratch that can be used to generate pseudo-salience labels for large datasets, and our proposed spatial attention guided models are highly predictive of the human attention and also are more accurate and robust than the baselines. More details are included in our paper. Thank you.